How's it going again, guys? Today we are going to be actually solving the differential equations. So from the previous video, we set up the differential equations for a rocket-propelled car, and in this video we are going to actually solve them. So this might take a little bit because there are a few steps, but let's get started. So we're assuming that the initial velocity starts at 0. We're also going to assume the initial position starts at 0, but that doesn't really matter, because we're just going to be solving for the velocity function, and then we're going to integrate the velocity function to get the position function. So we're not going to solve the position analytically, but we are going to solve the velocity analytically. And we're going to find a way to connect these two differential equations together, these two periods of time. So the first period, of course, is the rocket is expelling fuel, propelling the car forward, and then the next period would be when the car runs out of fuel and is just coasting along, just being subjected to air resistance, but it's not accelerating due to thrust or anything like that. As you can see, in the second differential equation, we have the mass of the structure because we're assuming it ran out of fuel completely. And we're left with the mass of the structure. So let's start off with this first differential equation. So remember that the mass does indeed change with respect to time. So remember to substitute that in. So we're going to get m naught kt. I'm going to have v dot, and on the right side we're going to have m dot, but we already explicitly wrote mass, remember, so finding that is pretty easy. It's just going to be negative k, right? The derivative of the mass with respect to time is going to be negative k. So that negative is going to cancel out with that, and it's just going to leave us with k dx. So all in all, this term right here is just going to be a constant. And then the air resistance term is left unchanged. So as you can see, writing it this way, the differential equation is clearly separable because we have just time here and we just have velocity here. Right, so what we're going to do is move all the velocity stuff on the left side and all the time stuff on the right side. So this is how I'm going to write it. V dot k vx minus c v squared is going to be equal to 1 over m naught minus kt. And then this v dot can be thought of as a differential. Oops. We're going to split this v dot into its differential components. On the left side, we're going to get dv. And on the right side, we're going to get tt. So quote unquote, we're splitting the differential, and then we're going to integrate both sides to cancel out that differential. But in reality, there is a proof that you can, when you integrate with respect to t of some time derivative of a function, that's the same thing as integrating with respect to the velocity itself. So you can prove it, you can do it more formally like that, but I mean, let's be real here. Splitting up the differential just looks a lot better, or just makes a lot more sense algebraically. So that's what we're going to do. So this left side is going to be a little bit tricky. This right side is going to be pretty easy. So when we integrate both sides, we're going to remember to put in our boundary conditions into the lower and upper bounds. So for the velocity, right, with respect to time, we're going to be thinking about what is the velocity and at what time, and what is the final velocity at what time. And that's going to be pretty easy. So we're going to say it's going to have 0 velocity for at 0 time, and this is just going to have some final velocity, which we'll call v rocket for this first stage, and you'll see why. So we're going to call the upper bound vr, so just some arbitrary vr that's somewhere in between the times mfk and 0. This will be vr, and you can just think of it as a range. So you can think of this integral as going from 0 to vr, and this is going to give us the final velocity of the rocket in the first stage. However, I get if that doesn't really make sense, because trying to fit the boundary conditions into the integrand bounds itself is kind of tricky to think about. It's easier to just think about doing the antiderivative of both sides and then just adding a plus c and then just fitting our boundary conditions into that arbitrary constant. But here we're going to do it like this because it's going to be actually a little easier. So we're going to get the integral from 0 to vr dv. So now our v kind of just becomes a dummy variable, and vr is actually the final velocity of the rocket. v squared. So on the right side, we are going to be integrating from 0 to time, as long as the time doesn't exceed mf over k, of course, of dt m naught minus kt. Okay. So this right side here is going to be pretty easy. It's just going to be negative 1 over k ln absolute value of m naught minus kt. Then we're going to be taking this from 0 to time. So remember, you can remember to think of this about as the dummy variable. So we're going to add primes here just so we don't confuse it with the actual time here. This is just a dummy variable. This is just what we're integrating with. And then here we're going to plug in t, and then here we're going to plug in 0. We're going to subtract 0. So we're going to do the negative 1 over k ln m naught minus kt. And then we're going to add, because we're subtracting, 1 over k, this plugged in, 0 plugged in. So that's just going to be m naught. So that's going to be the right side. The left side is going to be a little bit trickier, obviously, but you can solve it by doing a substitution. Something like this. So you're going to take the square root of k vx, and you're going to divide by c. And we're going to just call this u. And the reason why we're doing this is so we can simplify that denominator here. So our differential then becomes same thing here, vx over c du. So writing it like this, we're going to get the square root of kvx over c, which is a constant. We're just going to climb out. And then here we're going to, let's just ignore the bounds here. We're just going to remember that this is all going to be, we're just going to say this is u1, u2. We're going to resubstitute that v in, and then we're going to plug in the proper bounds here. But we're not going to solve for the u here at the moment. du, and then at the bottom here, so the whole point of doing that is, so when we square this, that c will cancel with the denominator here, and then that we can just pull out that k vx. And then all we're left with here is going to be 1 minus u squared. So that was the whole point of the substitution. As you can see now, we just have this beautiful clean 1 minus u squared. And we're going to just look at our table of integrals here and say that that is the inverse hyperbolic tangent. And let me just double check if that's correct. Alrighty, so I'm back. Indeed, it is the inverse hyperbolic tangent, so this whole thing. You can split this denominator into partial fractions and then solve it as a logarithm. However, we're just going to solve it with a hyperbolic tangent instead, because it's going to be just as hard to simplify for the natural logarithm solution as it is for the hyperbolic tangent solution, in my opinion. You guys can check that for yourself. If you want to split this up with partial fractions and solve that using the logarithm method, or solve that in terms of the logarithm, then you may go ahead and see if that actually makes the solution easier or not. But for now, we're just going to say this is the inverse hyperbolic tangent of u. Of course, with our boundaries plugged in, but we don't really know the u boundary, so what we're going to do is substitute the u back in. And remember, we're solving for u in this case, so we're just going to flip the square root sign and just going to take the reciprocal of whatever's in the square root sign and put a v here. That's going to be a solution. So here we're plugging in v equals 0 and vr. And the inverse hyperbolic tangent, remember this is the inverse hyperbolic tangent. I apologize that I just wrote tangent, because that is not the correct answer. The inverse hyperbolic tangent of 0 will just be 0, which you can see for yourself in a graph. I can show you the graph really quick. Let's go to Desmoth, and we get, oops, go. So this is what the hyperbolic tangent looks like, inverse hyperbolic tangent, and you can see that it is 0 at 0. So all in all, we're just going to get rid of this bound here, and we could just put a little VR here for the V rocket. And there we go. So we're going to write everything out. Alrighty, so here we have the full solved solution here. Of course, we're just going to need to solve for the V rocket here. So we do that pretty easily. So first off, we can cancel out these k's, which is going to be nice. And then we're just going to shift everything to the right. So all in all, doing all that, you may do this algebraically yourself if you want, but I already have the solution written down. So we have the V rockets with respect to time is going to be k vx over c. And then the hyperbolic tangent, not the inverse because we moved it to the right side, of the square root cvx over k ln m naught over m naught minus k t. And there you go. So this would be the solution for this first stage here, for this first bound. Now all we're going to have to do is solve for the second stage, so when it runs out of fuel. And luckily this differential equation is going to be much easier to solve. So we're just going to do that really quickly. And you can immediately see that this is separable, because ms is just a constant. Negative cv squared. And then we're just going to shift everything. So we're going to get dv over v squared is equal to negative c over m dt. So then when we integrate, we got to think about the bounds, right? So that's going to be the hard part of solving this differential equation. So when we integrate, so this lower bound, remember, is going to start when the rocket runs out of fuel. And this is going to be what the velocity would be the moment the rocket runs out of fuel. And that's going to be the v of rocket, right? But we're going to be plugging in that upper bound of time. So mf over k. And then the upper bound we'll just call vc, which will just stand for the coast velocity. So that's what we're going to plug in on the left side here. And remember, the right side is same thing. So at the end of the first stage is going to be the beginning of the second stage. And that's going to be precisely in the upper bound of t, which is mf over k. And then we're just going to go up to some whatever time, for whatever time. And then this dt kind of becomes a dummy variable here. So we'll just write it prime here so we can differentiate. And so on the left side, we're just going to get negative 1 over v coast plus 1 over v rocket mf over k. And then on the right side, we're just going to get negative cm t minus mf over k. So these integrals are pretty trivial to solve. And then of course you can see where I got this really complicated expression for my solutions. So if we go over here, so you can see this is the coast stage, and you can see that this part kind of looks very similar to this part, but I'm just plugging in mf over k as our upper bound, and that's why we kind of get that hyperbolic tangent on this right side, because we have to use the previous function, which is the v rocket, in order to solve the boundary conditions for this next period, which is going to be the coast period. So as you can see, this is exactly how you connect the differential equations together. And then what we do here is going to be solving for v coast, and you can do that yourself. It's quite easy. And then what you're going to do is just plug in mf over k into this rocket equation. And if you plug in mf over k here, you're going to just get the k's cancel, and you're going to get m naught minus mf, which is just going to be ms, the mass of the structure, right? So that's where I got that. If we head back, as you can see, what's in here is going to be m naught over the mass of the structure, because we're plugging in mf over k. So you may do that yourself. And then what you do after you have the velocity function is, in order to get the position function, we're not going to solve it analytically, but you can just plug into Desmos the integral from 0 to t of the velocity function dt. And here we're assuming the initial position is 0, but you may add some, I guess, initial position if you want to. And so yeah, that's going to be the solutions to this system.